Hello, Justin.
Hey, Brian.
How are you?
Good.
Ready for the final tomorrow?
It's ready as I'll ever be.
Ready as
I
yeah.
mean, I've got a few last minute questions for you, if that's okay.
Yeah, that's okay.
All right.
Uh, is it gonna be on the practice final that he gave, or what is it gonna be on?
Oh, it's on the practice final.
Okay. Let me pull those up. Let's see. Okay, A and B. Let's see. Okay, share screen. Okay. What was the first question you had?
Okay, so the first question was on problem, so it was number one,
Okay, number one. On A, section A,
section B.
section
Sorry.
B. Okay, section B. Let's see. Oh, that's too far. Oh, this one here.
Yeah.
Right. So when you see this polyol here, a lot of alcohols, and then at one of the ends is an aldehyde, or there's a ketone somewhere. This is just another way of showing carbohydrate sugars, right? Where
Hmm.
this end is the CHO part, and then this end here is the CH2OH part, and then everything in
Okay.
the middle is the OHs,
Mm.
right? Where you know how in this reaction here, the only thing that changes is that aldehyde to the carboxylic acid right there. Uh,
Yep.
wh- what weak oxidizing agent do you know that can do that? There's only three.
Um,
Or
I'm
first,
not,
the easier question is what oxidizing agent is super reactive that would oxidize both the top and bottom carbons of the sugar to the carboxylic acid?
I'm not too familiar with the oxidizing reagents.
Yeah, so for oxidizing agents, let's say we have sugar like this. If we use a strong oxidizing agent like HNO3, H2SO4, this is the one that would oxidize both the top and bottom carbon into carboxylic acids,
Oh, okay. Got it.
right? The weaker one would be three reagents. They would be Br2, water, and the other ones are um, silver ion, NH4OH, water. And then the other one that could do this is copper 2 plus NaOH and water. These weak oxidizing agents here will only oxidize the top carbon into the carboxylic acid. And this only works for aldoses. Like those three weak oxidizing agents only work for aldoses. They do not work on ketosis.
Okay. So it works on the aldehyde group.
Yeah,
Okay.
aldehyde group. But HNO3 does not care. It will oxidize both the top and bottom carbon to carboxylic acids. Whereas these three reagents here will only oxidize the top aldehyde carbon to the carboxylic acid here.
Got it.
Mhm. So for this question here, we are only oxidizing the aldehyde to the carboxylic acid, which we said A, B, and D could do that. But
Hmm.
C, it would also oxidize this primary alcohol, the CH2OH, into the carboxylic acid, right? So C is the answer here because C would not give this
Oh,
product
so it C creates a carboxylic acid of an
on this
alcohol?
end as well. Yeah, primary alcohol,
Okay.
right?
Okay. Got it.
Uh-huh.
And I have a few other questions. For number two, um, How come I believe it was between A and B. I think B was more acidic. Why is that? Is it because of the carbon?
Right. So the conjugate base of A would be that negative charge on that alpha carbon in between the two carbonyls there. The conjugate base of B is this negative charge on the alpha carbon in between those two carbonyls there. Right. The strongest acid is going to give the most stable conjugate base. Let's look at the
Hmm.
conjugate base of A. That conjugate base can do resonance in two areas with that carbonyl on the left side and this carbonyl on the right side.
Yeah.
The one on B can also do resonance on the left side and the right side as well. Right? But notice how on A, there's an OR group there that can also do resonance with this carbonyl here.
Hmm.
This O here is taking up resonance space, taking up resonance power, making that negative charge less stable. Right? So this B conjugate base here is more stable since it has all of the resonance space to itself, making it more stable. Whereas A has competition here. That oxygen there is taking up resonance power or space, making this less stable. Right? The more stable conjugate base comes from the more acidic acid.
Okay, so I guess the OR group makes it less stable as a base. Or sorry,
Yeah, less stable conjugate base. Right? Because the OR group there is interfering with the resonance that it could do with this carbonyl.
okay.
Right?
Got it. And just out of
That
curiosity, what if that was just an R group and we didn't have an oxygen there? Would that
oh
make it
without
stronger than B as an acid?
well, they're gonna be equal acidity then if there's no R group there and they're just R groups because that negative charge can do resonance equally on
Mhm.
both sides. So we can't tell the difference between those two.
Okay, so the main difference isn't the extra, I guess, carbon, because
No,
I'm looking at
no.
like the tertiary. It's the presence of what's the OR group,
Yeah,
right?
right. That's the
Okay,
main difference there.
okay. Thank you.
Yeah, no problem. But another thing is that if we compare the acidity of, let's say, an aldehyde versus a ketone, right? We know the conjugate base is gonna be like that right there. Then that's where the arguments take place, right? Which negative charge do you think is more stable? The negative charge on this or negative charge on this?
I say the negative charge on the ketone.
Right. So the ketone can do resonance with the carbonyl like that.
Hmm.
Also, the aldehyde can also do resonance like that, right?
Hmm.
Where at the ketone we have an R group. Is an R group an EDG or an EWG? Does it donate electrons or does it withdraw electrons?
I think that's an electron donating group, R.
Yeah, electron donating group, right? So if we donate electrons into that system, is that gonna make this negative charge stable or
Oh
destable,
wait, no,
less
this can be less
stable?
stable.
Less stable, right? So the more acidic thing here is this this aldehyde here,
Hmm.
because this hydrogen here is not an EDG, not an EWG. It will not affect this negative charge here.
Okay, so hydrogens don't count as an electron donating group or electron withdrawing groups.
Yeah, it's in the
They
middle.
can- okay.
It's the reference group. Yeah.
All right. Thank you.
Yeah, no problem.
I don't know if Joseph has any other questions. If he doesn't, I can keep going.
Yeah, you could wait, what? You could keep going.
Okay. I mean, I've got another question on 6A. And I can't help but say, hey, you have the same last name. My cousin. Woo. Sorry, no one's a very popular last name.
I think Justin is also a pretty common name.
Oh yeah, I have a pretty common first name and last name. I mean, if you try looking me up on Facebook, there's so many Justin
Oh
Nguyen's.
shoot. I think my MacBook is oh sorry. My MacBook is overheating
Yeah,
right now and
yeah, you froze for a sec.
yeah. Sorry, sorry. Yeah, I need to shut down my MacBook and let it rest.
Oh,
But it's getting back. It's getting back now. Yeah.
all right.
Right.
You good?
Yeah. Any other questions, Justin?
Oh yeah, it was 6A and I believe 6C.
6A and 6C. Okay.
Yep.
So when we see heat here and this ether here, right? What is this position called relative to the alkene? Is it vanillic, allylic, or
I think it was like
carbonylic?
a Lilac. I
Allylic,
mean,
right?
that's 118B.
Yeah, allele.
Is
How
this
about
118B reaction?
no. This is 118C reaction.
Oh,
But
is it
these are
Glycine?
just yeah, Claisen rearrangement,
Okay,
right?
it's Glycine.
Because what is this carbon here that dotted red? What is that position called? Vinyl, allele, copral.
Was it vanilla? No.
Yeah, vinyl,
Oh, okay, I
right?
guess right.
Because it's part of the double bond, so it's vinylic, vinyl, right? Whenever you have an allele, vinyl, ether, and you react that with heat, you do Claisen rearrangement, right? And I'm going to redraw this structure in a way that lets us see the mechanism much more clearly. Right. Does this make sense so far? Like how I rotated it and flipped the bond to
Yep.
get into this position here?
Yeah, I tried doing that, but I wasn't so sure on the mechanism.
Oh, right. So here's going to be the
Big part.
mechanism. Um, I'm going to make a new bond with that double bond right there. This double bond on the benzene is going to make a double bond with that carbon and oxygen. And then this bond is just going to break and make a double bond right there. After everything, this is what we get here. That double bond in the benzene is no longer there because that double bond made a double bond between that carbon and oxygen right there. Right? Does this make sense so far?
Yep.
Right. So from here, we usually end at this product if this carbonyl was not conjugated. You notice how at the starting material here, we have a conjugated aromatic benzene ring. We broke that aromaticity in the final product here. So what we got to do is aromatize, restore the aromaticity of this structure and get the alcohol back and the benzene back. Right. This is after the tautomerization step here to go back to the aromatic ring here. Right. What the mechanism is that some base will deprotonate this alpha hydrogen, make a double bond here, pop that double bond into the oxygen, and then that O minus gets protonated by some acid, proton source.
Okay, got it.
Right. So final answer here. Don't stop here because that's less stable than this aromatic ring here.
Okay, so yeah, there's tautomerization this step. Okay,
Yeah,
that makes sense.
tautomerization. Right.
Okay, and I wonder if we're in Glycine, does it always tautomerize? I don't think it
Not
does it?
always, not always, because if those double bonds were not there and these double bonds were not here, then it stays like that.
Okay, and let me guess, did we know to tautomerize because we broke the, I guess, the ring, the
Yeah.
benzene ring? Okay.
Right. If we broke it, we want to go back to it.
Okay, so that's how we knew how to tautomerize in that step. Okay, thank you.
Yeah, no problem.
And another question I had was on 6C.
Yeah.
So for this one, it looks like they're just adding an O, I guess, methyl group.
Mm.
I'm doing like, I think it's like SN2. But what I'm
Yes.
wondering is how do we know which chlorine that we replace?
Yeah, so this is not SN2. This is going to be a nucleophilic aromatic substitution on
Oh,
pyridine. Right? Where the mechanism is two steps: addition, elimination. Nucleophilic aromatic substitution. This is the chapter 25 material, the heterocycle material. Nucleophilic aromatic substitution, NAS on pyridine. Right. So let's just give you a general example of this pyridine here. When we do NAS by introducing some kind of nucleophile, it's always going to add at the second or fourth position here, where I'm going to say this is 1, 2, 3, 4, right? Never the third position. And the reason why is because when we draw in the mechanism, right? Let's say there was a leaving group at 4, which we do see in the problem there, right? The nucleophile will come around, attack that carbon. it does not kick out the chlorine because this is not SN2. SN2 reactions cannot work on sp2 carbons. This is an sp2 carbon, so SN2 will not happen here.
Okay.
Right. So what happens is this double bond here will go down and pop this double bond onto that nitrogen right there to get this structure here. Right, where the nucleophile is here and the chlorine is still there. Right. And then you notice how the negative charge is on the nitrogen?
Yeah.
That's what we want. That's a good thing. Which is why at positions 2 and 4, they are going to be where the nucleophile attaches to if there's a good leaving group there, because that allows for this nitrogen here to have a negative charge. I'm going to show you an example where if there was a leaving group at the 3rd position, there would be no negative charge on the nitrogen, right? But I'll show you that later after this one. The next thing here is that this negative charge on the nitrogen is going to go back, reform that double bond, shift this double bond over here, and then kick out the leaving group there to get to the final answer here.
Got it.
With the nucleophile substituting the chloride, but that was not SN2. It was addition, elimination, right? Where this is the addition step, and this is the elimination step here. Right. Let me show you the other example where it also works on position 2 if there was a good leaving there. Like let's say there was a Br here and we try to do like some kind of nucleophile like ethoxide, right? This nucleophile is going to attack that, pop this double bond to the nitrogen. That's the addition step there. You notice how there's a negative charge on the nitrogen? That's a good thing. That's what we want because that is going to be stable enough to exist for this reaction to go through. After the addition step, we do the elimination step. We go back to make the double bond there, restore the aromaticity, and then kick out that good leaving group there to get this structure here, where we have that new nucleophile there. Does that make sense so far? Right, and then Br just got kicked out right there. Now I'm going to show you why it does not work at position 3, even if there's a good leaving group there. Right, so let's say we have a chlorine at that position 3, and then we use some kind of nucleophile like ethoxide again. If we attack that carbon and try to go all around right there, right, this nitrogen would never have a negative charge, right? It's just gonna like you notice how the arrows here, like it would never land on the nitrogen. Like when I attack that carbonate there, when we try to shift the double bonds around, the double bonds would never ever land on the nitrogen. So in the resonance structure, nitrogen will never be negatively charged, right? Which is not going to be stable enough to go through. So no reaction. Right.
Okay, got it.
That's for pyridine NAS. For pyridine EAS, then it would go for the 3rd position. Right? Pyridine EAS. Where EAS reactions are like the 1,18B benzene reactions like halogenation, nitration, sulfonation, and your Friedel class reactions, Friedel class alkylation, Friedel class isolation. Because
okay, and those reactions are affected by electron donating groups and electron withdrawing groups, I believe.
These are gonna be affected by the positive charge, right? Because let's say this is position like 1, 2, 3, and 4. We are only going to add the electrophile on position 3. The reason why is because you know how nitrogen, we said it wants a negative charge because it's electronegative?
Yep.
For these EAS reactions here, they would not put negative charges in the ring. They will put positive charges in the ring, right?
Oh, right, there'll be electrophiles. Okay.
Yeah,
Yeah.
right. If we put the electrophile on carbons 2 or 4, when we draw out the resonance structures, there will be a positive charge on nitrogen, which is not good. That's not what we want because nitrogen is an electronegative atom. If we put the electrophile on carbon 3, you notice how like in the other reaction we did, whenever we try to do the arrows, there's never going to be a charge on N. Like there's never going to be a negative charge there. There's never going to be a positive charge there. Because when we do the resonance structures, we see the arrows never land there. Right?
Right.
So that's a good thing for this nitrogen because nitrogen does not want a positive charge, which is only available if we put the electrophile on carbon 3. So if we try to do like bromination, for example, Br2, Fe, Br3, that bromine would attach on that position 3 right there. Right? And I could show you the whole resonance of all these structures as well, but that's gonna be tedious and long time. But you get the idea, right? You get the general
Yeah.
idea. Yeah, that's right. That's different than these 5-membered rings here. The pyrrole, the furan, the thiophene, right? These right here, you only gotta worry about the EAS reactions. Do you know which position the electrophile would prefer to attack on? A or B?
I'm trying to remember. I think it might have been A or
Yep.
I think it was A.
Yeah, not B. The reason why is because A will give more resonance structures,
Hmm.
right? When we draw out the whole thing, that's the reasoning, more resonance structures. If we attach it to B, that gives less resonance structures, right? That's the important concept there. We don't have to draw out the whole thing because like you just got to understand like why it prefers to attach to A instead of B, right? Because A allows for more resonance structures compared to B. Right. So we have a pyridine here, which is a 6-membered ring with nitrogen involved in it. Right. And then this, if you have a nucleophile on the arrow, you know that this is going to be an NAS reaction. And we said that in NAS reactions with pyridine, what positions can it attach to? 1, 2, 3, or 4?
So I believe we're adding electrophile, right?
Yeah. Oh, nucleophile. We're adding a
Oh,
nucleophile.
nucleophile. Oh,
Right.
okay. If we're adding a nucleophile, then it has to be 4 or 2, I believe. But we have the
Right.
leaving group, so
Uh,
it'll have to be 4.
Yeah, right. It needs a good leaving group as well. We see at
Mm,
2 here, there's no leaving group, so that's why we don't put it there, right? We need a good
got it.
leaving group for NAS. For EAS, we don't need a good leaving group.
Okay.
Right. So
Just a
that's why,
curiosity, for EAS, do we kind of treat the nitrogen sort of like an electron withdrawing group, like we add to the meta position?
the nitrogen in the ring, don't treat it as an electron withdrawing group or donating group.
Oh, okay.
Right. But for NAS, right, the pyridine is going to be an electrophile because some nucleophile will attack that pyridine electrophile.
Mhm.
For EAS, the pyridine is the nucleophile that would attack any of these electrophiles here.
Got it.
There's one more thing that's very similar to the NAS on pyridine. It's the Chichi-Bobbin amination. Chichi-Bobbin, Chichi-Bobbin, Chichi-Bobbin amination. This one here is similar to pyridine NAS. The differences are that it does not require a good leaving group, and it requires a very strong nucleophile or base. And in this case, you're going to see NH2 minus, right? And you're going to see that in the form of KNH2 or NaNH2. Because whenever you see K or Na, that's always a positive charge, right? Positive charge on the K, potassium, positive charge on the Na, sodium, making whatever is attached to it, in this case, the NH2, the negative charge, right? The NH2 is a very, very strong base and nucleophile. So let's say we have this pyridine here, and we put that under KNH2 and ammonia as a solvent, NH3, right? The NH2 minus here is going to attack the second position, pop this double bond onto the nitrogen right there to give that nitrogen a negative charge. Right? But then this carbon here has a hydrogen that's going to leave as we reform the aromaticity here. Because that hydrogen is the leaving group right there, right? Not a chlorine, not a bromine. It doesn't need a good leaving group. That hydrogen is going to be the one that leaves. This is the Chichi-Bobbin amination reaction, right? It's very similar to NAS, but does not require a good leaving group. And the base or nucleophile we use is NH2 minus.
Okay, is there a preference for where we put the NH2? Like para
NH
or ortho?
Right. So it has to be either ortho like we did here or para. because it will
Okay, so it
allow
can
for a
be
negative
either
charge.
or.
Yeah, either or para or ortho, but not meta,
Got it.
right? Because meta would not give the nitrogen a negative charge.
Is there a preference for para or meta, or sorry, para or ortho? Or does either one work?
Either one would work, but
Both.
the ortho one would be way faster because when we go
Okay.
back for the elimination step, there's less arrows to crawl around and pick out the H.
Okay, so then
Right?
that should be our major product then, correct?
Yes, correct.
Got it.
Yeah.
Right, thank you.
Yeah, no problem. Your final is tomorrow at 8 a.m., right? That's early.
Yeah,
Yeah. Mine is like right after your final, 10:30.
the 30.
Yeah.
That's a little bit better.
Yeah, it is. It is. Yeah. Are you familiar with the midterm 1, 2, 3 new material?
For midterm 1, 2, and 3, I've been reviewing them, but mostly it's been reading over my notes to try and recall the
Yeah.
formulas. Mostly the only practice I've been getting, or the only practice I had time to review, was the final practice exams.
Yeah, that's
Um,
good. Yeah. Right. And then when
yeah,
you do those practice final exams too, like also try to make up your own practice problems and ask yourself what would change if you change that. And explain to yourself each the reason behind each arrow for the mechanism, and then practice
hmm
the mechanism for each predicted product as well, right? Because that could show up as mechanism for each predicted product question. But you have a note card, but on the exam, it will take a while for you to look at the look for the reaction in the note card unless you're very familiar of where to find everything in your card already. So that's why when you do these practices, practice the mechanism for each predicted product, and then as you do that, look at your note card and look for it in your note card so you know where to look for it during the
yeah,
exam.
that's kind of how I've been studying. I've been kind of reading over my notes in detail online and then trying to match them. All right, where is this on the note card? And then I've been doing the practice exams while using this note card in addition to my
Yeah,
notes.
yeah, that's good. That's
So
good. So you're familiar with it.
yeah,
Yeah.
and a lot of
hmm
color coding. Color coding really
Yeah.
helps.
Yeah, it does.
I see some people, I don't know how some people just have a completely black and white note card.
Yeah, I
See those and
know.
I get scared.
That's
Like, how do you
scary.
find anything?
Yeah. Yeah. Hmm. But after this, done in summertime.
Yep.
Yeah.
Any plans for the summer?
I'm starting chiropractic school in
Oh,
July.
nice.
Yeah. Yeah. How about you? You doing internship or anything or volunteering?
Um, I did sign up for a summer internship for the HRI system, so I think it's
Oh,
like some sort
HRI.
of surgical specialty unit. So yay,
Oh
no.
yeah, a surgical. Yeah, that's good. Are you pre-med?
Yes, I am.
I see. Yeah. There's a lot of pre-meds at the ATC drop-in table. Yeah. Like the
Yeah,
people who go, like they're a lot, they're mostly pre-med or pre-vet, pre-dental, uh,
I feel that's a
pre-PA.
requirement. You just have to live in the tutor center for pre-med.
Yeah. Yeah. All the pre-health people.
Well, they know
How
where to
many
get
are
help.
dental?
Yeah, Joseph is pre-dental.
How
Oh,
He
wow.
many are dental?
oh, how many are dental? Um, I've not as much as the pre-meds, but there's a good amount. Like uh people come and go differently each day, but I see one at least like once or twice a week, and some tutors there, OChem tutors, are pre-dental as well. I think you know one of them, Joseph. You follow him on Instagram, Andrew Tran. He's going to UCLA dental school. He's a tutor at UC Davis.
Oh yeah, I do know him. I've only met him once, and it was at a dental volunteering event.
Oh, at San Jose or
Yeah, it was San Jose. So he drove here like almost 2 hours just for the
oh,
event.
dang. Yeah. Is he starting the same time as Mohammed, the dental school?
Yeah.
Dang. Yeah, he's good. What year are you, Justin? Second year, third year?
I'm in my third year.
Third year. I see. Yeah, that's good. Wait, what's your major again? Oh, biological sciences, right? I think that
Yep,
you
got
told
it.
me. Yeah. Nice.
Still not officially decided what I want to do for pre-med. Still investigating.
Like
Hopefully internship
what
will help.
specific field?
I mean, part of me was kind of curious in cancer research,
Mm-hmm.
maybe even being a physician or physician assistant was kind of where I was thinking, just
Yeah,
because I
yeah.
like investigating and diagnosis seemed pretty interesting to me.
Mm-hmm.
Though I need to have the skills to make a diagnosis, so
Yeah, yeah. That's good. It's like outcome synthesis. Diagnose what reactions you need. Go backwards,
pretty
retrosynthesis.
much.
Yeah.
But the hard part is memorizing everything.
Yeah, yeah.
Like I can look it up, but
Mm-hmm. I mean, no card. Oh yeah, in medical fields,
I
yeah.
just have a note, giant note card.
In front of your patient.
Yeah, just pull a note card. Like
Yeah.
if A, it's this, if B is that, there's a
Yeah.
trick.
Yeah. The chat GPT it.
in ChatGPT.
Mhm. My final tomorrow is open note, so I just need to review my notes and make sure I know where everything is so I don't get lost in the final and then run out of time.
Yeah, notes are very helpful for these.
Yeah. Yes, Justin.
So I had a few questions on the final practice exam for section B again.
Yeah. Wait, let me. Okay, section B, question 4,
7A.
7A.
Yeah, it's on
This
the
one.
mechanism.
Right. Draw complete arrow pushing mechanisms for the following reactions. For part A, only draw the mechanism up to the bracketed intermediate. So we want to draw the mechanism from here to this bracketed intermediate only, and
Mhm.
not to here. Right. So that's a
Right.
note card thing where you you gotta put in that all those arrow pushing mechanisms to get from this amide to this
Mhm.
structure here, whatever this thing is. Like this carboxylic acid, amide together. Right.
Mhm.
Do you have that reaction on your note card? This is Hoffman
Um,
rearrangement. So the first thing you do is identify what is this reactant, which is a primary amide, the thing on the reagent, which is Br2 NaOH and water, and detect what reaction that is. That is Hoffman rearrangement from midterm one material. Once you find
wait.
that, then this question should be doable.
Okay. Wait. No, I don't think I have that mechanism on my note card. I should add that.
Yeah, I should add that on your note card, and then from there, it's just like copy and pasting.
Yep. If I can find the space for it on my note card.
Oh no, did
It's
you
already
already use all the space?
not all of it. I've got a little spot left.
Uh-huh.
I could maybe squeeze it in a few other
Yeah.
locations, but
There's
I
some
gotta
word
find the
migration
right,
steps in
yeah, I
there.
gotta
Like,
find the right balance of,
mm-hmm,
having it small enough where it fits, but not
mm-hmm.
too small to the point where I can't read
Can't
it.
read it, yeah.
Yeah, I had one classmate, she glanced at my note card, was like, how can you read that? And I'm like, well, I wrote it.
Dang. Oh my
I
God.
I have to wear my reading glasses for this one.
Yeah, you put the paper up to your eyes.
I actually do.
Oh my gosh. The TA is looking at you like, oh my God. Are you planning to become an OChem tutor when you finish or no time? Like you got extracurriculars, other classes?
I mean, I don't know if I have the I mean, maybe depending on like how I select my courses for
Mm,
next year,
mm-hmm,
but I don't know if I have like the grade to become an OChem tutor because the biggest, issue I have is memorization. Like I can explain some of the mechanisms if I
mm,
pull up my notes,
mm-hmm.
but that's probably about it. I don't
Yeah.
know if they'll accept me as a tutor.
If you apply, the interview is not that bad. They'll send you videos to watch and make sure to watch them because they'll ask you questions from that, to make sure that you watch them. The mock tutoring session is like okay as well. Make sure you teach by asking questions, like not just give them the answer straight up. Um, give practice problems, like similar practice problems related to the concept, and have them do it instead of you like doing the practice problem for them. Like walk them through the problem and like guide them through it, and then
Mm,
give positive reinforcement every time like they do something good as well, right?
okay.
And then
So,
whenever they get something wrong, don't just be like you're wrong. That's not how you do it. Try to validate their thinking and reasoning why they chose the answer and be like, oh yeah, that's a common misunderstanding. I can see why you thought of it like that, but um, this is actually what's going on here, and then
mm,
teach them from there, right? And then after that, like once you get hired, like there will be some things that you like forgot about, like how when I started tutoring, I had to use my notes a lot, look back at my notes, ask other tutors for help.
mm,
But then the more that you tutor, the more you see things over and over and over and over again, the more it will click and stick. And then you don't have to look at your notes anymore. Things start making more sense. You connect the dots like from different
mm,
things more. You have a deeper understanding of each material. And then whenever you see a new kind of problem, like you always break it down to the fundamentals and then see what you can do from there, and something will click hopefully. And I'm still learning things like every time I tutor people, like I gain new insights and perspectives from how people think
Mhm.
about the problems, and then I use that to help other students to think the same way as well, and it helps them too. I'm still learning like new perspectives and insights as I tutor too.
Yeah.
Mhm.
Okay, I guess then for 7A, I should just look up the mechanism for it.
Yeah, yeah. Look at the ways.
Okay.
I gotta look at the notes for this. I'm not too sure of like the arrows of what it starts with. And there's some weird migration stuff in there too, but it's a mechanism note card thing,
Got
right?
yeah, I would definitely be adding that to my note card tonight. I know they say, hey, get a proper night's sleep, but I gotta add this to my note card, so I don't know if
Yeah.
sleep's an option.
That should be your last thing. Like add this mechanism to your note card and then go straight to sleep.
Yeah, I mean,
Yeah.
I want to keep reviewing more notes, but I think I might just have to sleep.
Yeah. And
Sleep
if
might
you
be more
wake up
important.
early tomorrow, then you could like briefly go over some things before the exam.
Yeah, that'd be smart.
Mhm. It's at Rock Hall, right?
Yeah, it's at
Yeah,
Rock
yeah,
Hall.
yeah.
Thank
Rock
goodness it's
Hall.
not in a weird spot on campus. My last final for Chem 118B was actually on a rather outskirt part of the school. So I
Yeah.
had no idea where it was. So I left like really early along with a bunch of other students.
Uh-huh.
And I passed the cow pen
Yeah. Oh my
on my way
God.
there. And it's like, yeah, this is definitely a place I haven't been before.
That's like going to adventure, new place to take the final.
Oh yeah, it was an
Yeah,
adventure.
yeah.
Even got to like pet the cows on my way back. I'm like, all
Oh my
right,
God.
sweet. That's my break from
Yeah.
finishing. My
Mhm.
reward is paying the cows.
Yeah, yeah. But the one in TV final I heard last quarter was very rough. Like he put some weird questions in there.
Yeah, I think it was really rough because the last the last week of material was rushed. We ran out of
Yeah,
time.
yeah.
So we had to go through lecture videos for that. And a
Mm-hmm.
lot of us really didn't have enough time to fully understand what that material was. Like I
Mm-hmm.
was just finishing my notes, so I didn't really have a lot of time to practice or review. It was mostly just like get the new material down because they're gonna test a good chunk of that on our final, and that's what it was. So
Oh,
a lot of
dang.
us didn't really know fully what we were doing.
Yeah, I know it was rushed. Like I don't what you guys like
Yeah.
well, usually the end of 118A and 118B is really rushed. Like 118A with all the alcohol, Grignard, ether stuff is rushed. 118B, the Aldol, Michael Robinson annihilation stuff is rushed. And then 118C, the end is much more chill and smooth. Like the end of 118C is slow.
Yeah. Actually,
Mm-hmm.
yeah. I mean, looking back, yeah, 118A and 118B was rushed for me.
Mm-hmm.
Both Nasiri ran out of time, and there was the
Mm-hmm.
PCC and Jones that was rushed at the very end.
Yeah,
And then the
Grignard.
enolates for 118B that was
Yeah.
rushed.
Uh-huh. And then
Yeah.
Helix finished like ahead of time. Like he had time to like do practice runs for the final too.
Oh yeah, our last two, I think, lectures was just review
Mm-hmm.
sessions, so very
That's good.
chill.
Yeah, that's good. And that's a
Yeah.
segue to biochem, like with all the amino acid, peptide, DCC coupling, bulk, CBZ protecting group. That's a segue for biochem when you take
Interesting
biochem.
enough, the amino acid stuff I actually enjoyed the most out of this
Yeah.
OChem so far.
Yeah,
Hopefully I'll enjoy biochem.
I think you will. Yeah, if you do like the amino acids, the
Well, I like
section.
bio, so
Yeah.
wait, is there if I ask you a few synthesis questions for
Yeah.
the final?
Hmm.
So there's like 8A and 8B. Let's start with 8A.
Okay. So what functional groups do you see on the products here in this molecule? What are the functional groups that you see?
So I see an ester,
Hmm.
looks like a ketone,
Yep, ester and ketone.
and then looks like maybe an what's it? Not methyl ethyl group.
Ethyl group, ethyl. Right, but the ethyl group is just an R group. It's not
Hmm.
considered a functional group. It's just a hydrocarbon chain. Right,
Okay,
but that is an ethyl group there. But the functional groups are ester and ketone. Right,
got
and
it.
this is an ethyl group. What is the relationship between the two carbonyls here? 1,1, 1,2, 1,3, 1,4, or 1,5?
1,3.
1,3, right. And what reaction do you remember that makes a 1,3-dicarbonyl?
I don't remember the name. Gotta look at the note card if I
I'll
can
give you a
find
hint.
it.
Starts with a C.
See, oh wait, was it? No, it wasn't Glycine, was it?
It is
No.
Kaizen. It is Kaizen.
Oh,
Yeah.
was it
Kaizen.
Glycine?
Right. Where the one with the OR group, right? The alpha carbon of that is the nucleophile, right? Because the ester is always an ester, like the
Mm,
electrophile is always an ester with the OR group. This dot carbon that I dotted right there is the carbon. It used to have an OR group, but you know how for Claisen the OR group gets kicked out in the mechanism? That's why it's no longer
mm,
there,
okay.
right? When I make that cut right there, I'm gonna see that we had these starting materials here, where the star is that one, and then the dot one is this carbonyl here, where it also used to have an OR group like that.
Hmm.
Right. You notice how these two esters are the exact same because the OR group is the exact same OR group as the other ester here. The R group on the ester, 1, 2, 3, 4 carbons long, is the exact same, 1, 2, 3, 4 carbons long. These are the exact same esters here, right? So
Got
we
it.
could do self Claisen condensation by introducing base and water, NaOH and water, right? Because the first thing is to deprotonate this alpha carbon to make that into a nucleophile here, which is just going to attack another version of itself and then do the whole Claisen mechanism to get the 1,3-dicarbonyl here, right? Where one of the O groups will just leave.
Okay.
Right. Now we got to figure out a way to make this ester from this starting material here. Right. You notice how at the original molecule here, we have 3 carbons, and then in the starting material, we have 4 carbons here
Hmm.
before the carbonyl. Let's say this ester came from a carboxylic acid because that ester is a carboxylic acid derivative, right? What reaction do you know that can make a ester from carboxylic acid here?
Let me think here. Acidic makes that. So, I mean, I'll need to check my note card again. I don't remember off the top of my head.
Yeah, there's
Starting.
multiple ways to do it. You could do Fischer esterification where the ester you want, you could use CH3OH acid and heat.
Oh, right. CH3.
Yeah,
Okay. Yeah.
where the CH3OH is the CH3OH part right there. Now, do you remember the two methods that could create carboxylic acid with an extra carbon from Mitim 1? Like, what are the two ways to add an extra carbon where that extra carbon is the carboxylic acid? There are two methods.
I believe we can do. What's it? I mean, I'm thinking like more like converting alcohols into carboxylic acids, but I don't think that's it. I was
Yeah,
thinking like PCC Jones sort of. Well, not
well,
PCC.
Jones from this primary alcohol here, but how do we get that extra carbon there?
Um, could we form maybe a nitrite?
Nitrile, right? We could do NaCN
Hmm.
to convert that bromine to a nitrile, which this is the extra carbon right here. How can we convert a nitrile into a carboxylic acid?
We can react with water and heat, I believe.
Yep, acid, water, and heat. H2SO4, water, and heat. Hydrolysis of nitrile to
Hmm.
carboxylic acid here. The other way was to do the Grignard route, doing Mg to create that into a MgBr, and then that would attack carbon dioxide gas, CO2. Oh, not gas, but carbon dioxide, and H plus workup, right? Because carbon dioxide is gonna look like this right here,
Hmm.
um, where the Grignard can attack this carbon here, pop the double bonds with oxygen to become the O minus, and then the O minus gets protonated to become the OH here, right? Where this C is the C of the carbon dioxide there.
Okay.
Yeah, that's the other way right there.
All right.
Yeah.
Thanks, Brian. I have
Yeah.
one final question.
Mm-hmm.
So it was on 8B. I'm wondering,
Yeah.
does this I think there was like this one reaction. I think it was
Mm.
118B we saw, but I think there was a way to convert NO2 to NH2 groups.
Yeah, it
I
is.
wonder, is that the first step, I believe?
Yeah,
Because I
that's the
know we
first
can
step.
convert an amide into a carboxyl. Okay,
Right.
so wonder how
H2PDC.
should I be reviewing all the 118B material as well, or how
Not all
much
of
of that
it.
should go?
That's the benzene stuff, like bromination, chlorination, sulfonation,
Mm,
Friedel-Crafts reaction, um, and then like the directing groups, EDG, EWG, what takes priority over the other to direct the group for the benzene synthesis.
okay.
Yeah,
I
those
guess
things
yeah,
are
I
gonna be
should
important.
probably add the reactions to convert the
Yeah, and
what is it? The substituents like NO2 to
mhm,
NH2, and I think there's another one too.
yeah, the carbonyl into just an alkane, like
Mm,
like benzylic carbonyl to an alkane, and going backwards as well, like NH2 to NO2, and then from a benzylic carbon to back to a carbonyl. Those interconversions are important as well between the
got
ortho para director, meta director. Those things are important,
got it.
right? Where we could say that this can come from a nitrile. And then we said earlier, we could hydrolyze that nitrile using acid, water, and heat to create that carboxylic acid there. But this nitrile here could come from the N2 plus or N2Cl, Sandmeyer reaction from CuCN, copper CN, right? But to create that N2 right there from NH2, we're going to use Na, NO2, HCl, 0 degrees Celsius water, right? That would convert this NH2 to N2 plus or N2Cl because the Cl has a negative charge. And then from this diazonium salt here, we could do a whole bunch of reactions. We could do CuX, where X could be Cn, Br, anything you want to add. In this case, when we want to add a nitrile, we do CuCN. And then once we have that nitrile there, we hydrolyze that nitrile into the carboxylic acid here.
So I'm sorry, what did we do for the other reaction? So we put NaNO2, HCl, and we create a what was it?
Diazonium salt.
Diazonium salt. Okay.
Right, where that could do a whole bunch of reactions.
Okay, and then we replace with a cyano group.
Yes, and then we
Oh, and that can
hydrolyze.
also go. Oh, and we can also create carboxylic that, so it doesn't have to be an amide. Oh, okay.
Yeah, right.
All right. Thank you.
Yeah, no problem. Yeah. Oh, hey Ryan. I thought you said you're gonna sleep at 6 p.m. and then wake up at 4 a.m.
My my dad came home with pizza, and then I was
Oh,
like, "Damn,
and he woke you up?
yeah."
Dang, wait,
But I
when did
need
you
to do
join?
this. I need to like do this consistently for a week before I start posting it, because then then I'll know like if it actually works or not.
Yeah, 6 p.m. to 4 a.m. That's like 10 hours of sleep. Like 6 hours,
Yeah,
yeah, 10 hours. 6 p.m. What the heck? Wait, when do you eat dinner then? Like if you sleep at 6 p.m.
I don't eat dinner.
You
I
don't eat dinner.
I sneak. Basically, my mom sleeps on the couch, and then like the kitchen is like across from the couch. So I literally have to like sneak like freaking Cheerios out of the kitchen into my room.
Oh, what the heck? So
Y-
do you eat breakfast though, at least?
Yeah.
That's good. That's good. That's good. Wait, so you eat Cheerios for lunch or?
Um I guess I have to sneak because I don't know why, but like my mom just like sleeps on the couch, and I'm like,
Huh?
she should sleep somewhere else, because then like if I open my refrigerator,
Uh-huh.
the refrigerator light will just like wake her up, and like that's no good. So I literally have to like Mission Impossible my way out of it.
Oh, so you don't want to make you wake your mom up from sleeping.
Yeah.
I see, I see. That's interesting. And then your dad like just came home and woke you up to eat pizza?
Yeah.
I see, I see. Dang.
I don't know. It's like almost like, because on the calendar it says like you don't have any more days tomorrow
Oh yeah,
either.
I canceled it tomorrow because I'm going to an event, and then on Thursday I'm having a party after finals. And then on Friday I'm doing a graduation photo shoot for pictures. And then Saturday that's when I graduate. And then next week is I'm gonna take a week off next week because that's my summer break and before summer school starts. And then once summer school starts for UC Davis, that's when we resume the office hours, right? But then during that week, I'll check your posts and try to be consistent with the thing. But if it doesn't work, then don't follow with that plan, you know. And we'll catch up that week when I resume the office hours, and then we can catch up and like talk
But
about
I'm kind of
talk about
glad that
your
I met
plan.
you today.
Uh-huh.
Yeah.
Yeah. Like before that like whole break, that whole week break, next week, and then go back. Yeah. Wait, when did you join this office hours? Like what time?
Like 5 minutes ago, maybe.
Oh shoot, yeah. Good thing you joined. So then the next time we're gonna see each other again, or like when I resume this office hours, it's like around 2 weeks from now.
Yeah.
Yeah. But yeah, we'll catch up and see how it goes, right?
Mm-hmm.
Yeah. Uh-huh. Okay. What's your plan now? Are you gonna like go back to sleep, eat pizza?
No, I think I'm gonna actually start like consistently doing it because I was like kind of worried because I'm gonna miss the 9 p.m. calls. Oh no. And then
Yeah,
yeah.
I see. See, like, see if it works for you first, and then if it works, stick with it. If it doesn't work, then you can always just pivot and adjust.
I'll just do it for a week,
Mhm.
like consistently, and then if I know I keep doing this forever, then
Uh-huh.
I'll post it. But I need to start doing it for a week and then
Yeah. And that week is when I'll take the break from office hours, so that's perfect.
mhm,
Yeah, right. But if it works, then just stick with it, and then you don't have to like go to these office hours if you sleep 6 to 4. Yeah.
mhm.
Mhm. Right. I will and let me know on school as well, the DM school, how it goes. Cause if it works, then you probably not go to these anymore, but just DM me on school if it works.
Mm,
Yeah.
mhm.
Uh-huh. Well, I will see you guys next time. And Justin, good luck on your final
Oh
tomorrow
yeah,
Yeah,
8
when are
Brian.
a.m. Yeah. Yeah, no
when,
problem.
when, when are finals?
His
Yeah.
final is tomorrow 8 a.m.
Oh,
Yeah, so I'm debating, do I sleep or do I study?
What's your advice, Ryan? What would you recommend him to do?
mm, I mean, I usually study before all my tests, and I usually come there like sleep deprived, but it really doesn't matter because I always gotten like an A already, and I don't know.
Oh yeah, Ryan, for his finals week, because he's a high school student, he said he pulled like 2 all-nighters.
Dang, I can't pull all-nighter.
Uh, yeah.
Mm,
I mean,
Don't do that.
I can stay up late to some degree, like maybe
Mhm.
run on 6 hours of sleep, but like I run on caffeine and adrenaline, like that's what I need. I need
Yeah.
food and I need caffeine. Sleep, it's recommended.
Yeah,
But,
it's recommended, very recommended, but hard.
all right.
I run on. I don't. I'm trying to like run it in like 4 a.m. without coffee. Yeah, I don't
Oh,
drink coffee, so
yeah.
Like, I mean, you
Dang.
could try something lighter. I mean, I don't drink coffee, but I drink like this chai tea. I found it at
Tea
Costco, and it is have caffeine on it, but I don't think it's as strong as coffee.
hmm,
or some matcha latte, basic.
Mm, yeah.
hmm,
Actually, I know there are some teas with caffeine, where they don't give you like the tea bag, they give you like the actual tea powder itself. So like you can control how strong you want it to. I kind of like those. Like say, oh, I'm really tired, I'll add more, make it a bit stronger, add less, make it a bit lighter.
hmm.
Mhm.
When I'm tired, I usually like get like those like I forgot what's it called like when you like getting eating pho at a restaurant, right?
Mm,
Mhm.
But like instead, I just put water in it, and that's like my water for like that one meal, like breakfast, lunch, dinner. So it's just water.
mm.
That's it.
Mm. I
Uh,
see, I see. Dang. Well, I'll catch up with you guys next time. But I know Justin, he's probably not gonna join back because he's gonna be done with OChem.
I
But
mean, wait,
yeah,
just how much do you have to study?
but me, well, it's mostly a bit of review. I've mostly been doing practice problems when I can for the past few days. So I'm probably just gonna do a quick review, maybe add a few things quickly to my note card, and then just try to get as much sleep as I can. So I'm probably gonna go now and
yeah,
work on that. So
Did
yeah,
you
thank you so
brush your
much, Brian,
brush your
too.
hmm
You've
shower yet?
also helped a lot
yeah.
on
No
saving my
problem. Good
grade.
luck.
Did you
Good
take
luck
a
with
shower
all your
yet?
future endeavors too.
Thanks, friend.
Hmm.
Bye.
Justin, did you take a shower yet?
Wait, what? Oh, me? No, I'm probably about to refresh and then get back to work.
Uh,
Yeah, I've been running around campus all day, so.
Yeah,
I'm
it's so
not
hot
going.
too. Like Davis is like I'm sweating so much right now.
Oh yeah, same here. I mean, if I had a camera, you would see me just sweating. I'm not gonna lie, I literally look like I'm going out on a savannah. Because I look like one of those like 1930s explorers or Indiana Jones characters. Like I'm wearing like I think I had like a silk scarf and I had like a just like all beige or gray colored outfit
Oh my God,
or
yeah,
sand
yeah.
colored.
I know, like I saw you wearing like all like sleeves and like long pants, and I was like, how are you wearing that and this hot weather?
I mean, I'm wearing pretty light pants, but it's also because it's freezing inside the library. It's really cold because
Oh
they
yeah, yeah,
cranked
it
the
is, it
AC.
is.
So like I have to find that
Yeah.
right balance. If I get too cold, then I start I can't focus. Plus, like I said, I run on adrenaline and caffeine, so I literally get more hungry faster. I need the calories for studying. I don't need the calories to keep me warm.
Yeah.
I usually run better in the cold, and then like
Yeah.
because like I usually study shirtless. I realize that it helps me, and then I don't know what like helps me like keep going through like studying. I haven't figured out what that is yet.
You still got time, like to find out
Yeah.
your studying preferences and everything. Yeah. Time to experiment.
Yep.
Yeah, because I usually crash when
Well,
I eat
I will
like
see you guys.
carbs. So yeah,
All right.
yeah.
Bye,
See ya.
Brian.
I'll tell you about
Yeah.
it
Bye.
next
Bye,
time.
Justin.
Bye
Yeah.
bye.
Yeah. Bye
Uh,
bye. See you,
bye bye.
Ryan.
Bye bye. See, I'll talk to you
Yeah.
later.
Yeah.